education and governance within the U.S. And others places. So our goal is very simple. We're going to just go through a number of wireless case studies or use cases just to provide you a better understanding of how wireless technologies are applied in the business. As you all know, wireless is a part of everything we do every day. If you just count the number of wireless devices in your home now versus, let's say, 10 years ago, you've seen the explosive growth. My kids expect wireless connectivity whenever they go somewhere, as do we. So we're going to go ahead and, with that goal in mind, just do a quick introduction. So I'm Bryan Brown. So I lead, as mentioned, a team of systems architects focused in on government and education. My use cases today are connected vehicles and healthcare. I'll be followed by Jeff Whitmore, who's a systems architect on my team working out of Michigan. And he's going to go through higher education use cases, large lecture halls, dorms, and then also talk about some other interesting examples for farms, as well as stadiums. Matt Virus is on our Internet of Things team. He's a technical solutions architect. He's going to be talking about wireless within K-12 city governments and using those technologies to bridge the digital divide. And then James Sands, who's a systems architect on a Meraki team, is going to wrap things up with some insights into an installation that we have at Sweetbriar College. So when we look at where we're at with connected vehicles, there's a variety of technologies that we're using to connect vehicles at the roadside as they travel down the road. So this chart basically shows now you have your smartphone in your car. When you're in your car, you're using that smartphone to stream audio and to stream navigation, right? So right now, today, that average use data volume for a smartphone while you're commuting, based on the average commute of 43 miles in 54 minutes, that average stream is about 295 megabits, right? Which equates to about 5 cars usage of volume as you go down the street, streaming music, streaming navigation, and providing some telemetry back up to the manufacturer for that car. We're continuing to see that volume of data traffic grow. It's projected by 2024 that an average vehicle will be using 8.3 gigabits of data during that commute cycle of 45 minutes in the same distance of 45 miles in commute time of 55 minutes. So basically, we're seeing the trend reverse, where a car is going to start taking up more data on the average commute than 5 cell phones would. The prior slide showed that 5 cell phones or 5 cars equated to 1 cell phone. So we're starting to see that traffic increase to the vehicle. And we're using that traffic, we're going to start seeing it used for what we call ADS, or Advanced Driver Assistance Systems, right? And those are systems like electronic stability control, anti-lock brakes, blind spot prevention systems. The things that we're seeing in vehicles are going to be starting to report those types of things back to the roadside so that we can predict when traffic slowdowns are going to occur, when road conditions are getting messy, if anti-lock braking is being applied by a number of vehicles on the roadside. And this is all done through wireless connectivity from the vehicle to the roadside, which then goes back into some type of analytical engine processing. As we move forward with connected vehicles and autonomous driving systems, we're going to again see that volume of traffic go up across the wireless. We're seeing that cars can actually generate 200 to 250 gigs of traffic per hour based on the ability for these autonomous vehicles, self-driving vehicles, to communicate back and be communicated with from the roadside. So these are some of the interesting use cases for wireless technology, both cellular and wireless, traditional wireless Wi-Fi capabilities. You're also seeing with the connected vehicles that we're connecting all the infrastructure that vehicles use as well, the service stations, the fuel stations, charging points, again, roadside infrastructure, smart parking, so the vehicles can actually communicate directly to the smart meters within a city, right? So you don't have to go into the app and register. It'll automatically connect to your vehicle and know where it's parked within the city and charge you appropriately. The next use case I'm going to talk about is in healthcare. So we're seeing 80% of clinical folks, doctors, nurses, want to use their cell phone when they're in the hospital, and you not only use it to make calls, but use it for medical applications. So that's an important stat, right? Because we need, while they're in the facility, that personal device now becomes a medical device. It's patient charts, interactions with tracking, being able to access medical information. It becomes a very important part of the day-to-day doctor-patient interaction. So you have to make sure that your environment is set up and prepared to provide that, because it's all done through wireless. And again, the phone could be connected outside to the LTE or phone company, but inside it's connected to the wireless network. So in architecture, in this use case for a hospital, you'll see the access points, which are connecting, in this case, iPhones. This healthcare provider actually standardized so that all the doctors and nurses would use Apple iPhones. This helped them guarantee performance, because if they open it up to everything, every type of endpoint device, it would be very hard to do that. It connects to the access points, which connects to switches, right? All wireless at some point connects to the network, to switch and routed architecture. Goes down into the core and communicates with the wireless controllers on the back end. So this is just a pretty standard environment for wireless, right? Your access points are connecting your endpoint devices and then running them back to some type of centralized controller systems. But in hospitals in particular, you want to make sure your coverage models are mapped very well. So in this case, having the antennas visible allows them to get the broadest spectrum out to the end user and the best connectivity. They also did this and arranged each of the APs so that their cell sizes would be effective based on speed that they were looking to drive to the endpoint, in this case around 30 megabits per second. And they used directional antennas in some cases in order to make sure that the wireless coverage was the most impactful going across. So with that, there's your use cases for connected vehicles and in healthcare. I'm going to turn it over to my good friend, Jeff Whitmore, to talk about higher education, high density auditoriums.
Hi, I'm going to go over some use cases today that I've worked on recently. And like Bryan said, we'll start off talking about an auditorium. When you haven't, Bryan, how do I make the slide? I'm sorry.
If you
Just
look
over
up
to the left, there's
I got it. Sorry about that. So if you have an auditorium, you have like 500 and some people. Obviously, one access point could cover the whole auditorium, but if you had 500 people connected to it, it's not going to work that good. And also, if you were to put omni antennas in here based on experiences, they won't work that good too, because with an omni antenna, you could have a user sitting here and they could connect anywhere in the room. And one of the items that you want to do with an auditorium is you want to design for capacity as much as coverage. So you want your users to connect close to an AP. And one of the ways that we found from experiences is to use directional antennas like Bryan talked about, where we can contain the signal in a certain area of the room. One of the issues that we've seen in colleges when they've put omni antennas out in the hallway, because before a class, a lot of times students would congregate, let's say outside here, and then when they walk in, they'll stay connected to the omni antennas out in the hallway, and then they would have a poor experience. So we've moved outside the hallway the antennas back, and then inside the auditorium, we've put several access points with directional antennas facing down. And also this design is for 5 gigahertz, because 5 gigahertz will give you a much better quality signal than the 2.4. The 2.4, you have 3 non-overlapping channels. If you were to put 12 access points in this room on 2.4, you'd have contention issues and a poor experience. So we use directional antennas and lower the power level of the APs facing down. Let me go to the next slide. And the design would look something like this. So in that room of 500 people, we have 12 antennas. This is what the directional antenna is. It's contained to a certain area, and I'm just pointing an example. It's a square, so it'll cover around a 40-foot section here, and that way the clients will connect hopefully to one of the closest access points versus connecting across the room. The other thing you'll notice here, here's a heat map. We turned off almost all of the 2.4 access points. We do not want our clients connecting on 2.4 today. Almost all clients today support the 5 gigahertz. And again, it's because of the number of non-overlapping channels we have. We can have a much cleaner spectrum. And then this is modeling software that we used when we built this design. One of the best modeling tools is called Ekahau. There's also Air Magnet. They both work well. But we can model the entire design, and it does the actual channel plan. And we also, for the power level, we turn the power level of the APs down to 11 milliwatts to match the client, like an iPhone. Its power output is at 11 milliwatts, so you want the access point and the client to match each other. The problem can be if you have the power level too high from the AP, the client can hear the AP, but the AP can't hear the client back, and it causes a lot of retries and poor performance. So that's what we want to avoid. We want to match the power level of the AP when we do our site surveys. We, like I said, we kept only 3 access points on 2.4. We turned the rest of the 2.4 radios off. And this design works quite well in a room that large. So we're trying to keep it around 50, 55 users per access point. And the design, we also have like our design guide published out on the Cisco website. And the design, you know, it's a guideline to follow. It does take a little bit of art, but this design guide has a good coverage of how to do these high density designs. Next use case is just a regular classroom design. Real simple, like on a normal classroom, like in a K through 12 school, or in a normal lecture hall in a college, you can get away with 1 to 2 access points per room. And these would be like a normal size room. Here you can see is another auditorium where we have more of the high density design with the external antennas facing down. And then down here we have professors' offices. So we have a access point about every other room, and the bleed through will cover the rest of the areas, the offices in between. Then this is a typical dorm room in a college dorm. And we like to do 1 AP every other room. And then also the floors above and below you would want to stagger. So like if you have an AP on floor 1 on the floor above, you might have it moved over here. Dorm room APs, these are called the hospitality AP. They're used in dorm rooms and on cruise ships. These are meant to be mounted vertically. And one of the reasons why we choose this for a dorm is because college kids like to plug in Xboxes and printers. I mean, today most of them have a wireless card, but it gives them the option to plug in if they had to plug in. One thing this I always say when you site survey, make sure to site survey with the access point you want to deploy. I have seen at this very large college, this access point worked very well in the dorm rooms, but then they tried to use it in an apartment building complex that the college owned, and it didn't work well at all. And if they had done a site survey, they would have found that they should have used a enterprise access point. So keep that in mind whenever you are doing wireless, always survey with the access point that you're going to deploy, because there's blockers and stuff out there that you can't always see. Another for this large university use case is they have a very large working farm. So there's a lot of farm buildings around, and there's fiber connecting a lot of these buildings, but there's buildings that are outliers that have no fiber. Running fiber to every building would be ideal, but it's very expensive. So in order to connect some of these remote buildings, they're connected wirelessly back to like a point of presence here that has an internet connection or a LAN connection going out. But what this will do, for example, in this example, they have like a horticulture building, and then off this building they have other buildings, and it allows them to have that internet presence when we're not able to run fiber out here. And they can also, some of the use cases is to do classroom teaching. With the pandemic, students weren't always able to come on campus, so this would allow them to do teaching via WebEx. One of the things, some of the design considerations when you have outdoor wireless, using this mesh, you do need a clear line of sight. You also need to take into consideration any growth from vegetation. I've seen outdoor networks put in, and then 3-4 years, trees grow up, and then the signal doesn't work very well. And outdoor is also very susceptible to interference, so a site survey is very critical when doing outdoor mesh. And here's an example of a blow up of a building that we recently did a design for. So they have it's a teaching farm, so they have horse barns, chickens, all kinds of stuff like that. And for this a swine bar, because of the pandemic, they wanted to stream WebEx to do classroom teaching. So here's just like a simple design that I helped them put together with access points. And one of the requirements, which was interesting because I'd never done a pig barn before, was that the access points needed to be able to be power washed too, and then be able to sustain. These are things that sometimes we don't think about when doing designs. Wide temperature swings, so they have to be able to get cold or get up. Our access points, our outdoor ones, will go up -40 below Celsius and up to 120 degrees. So these access points have a quite wide temperature range. One of the opportunities I had a few years ago, it was one of the more complex wireless designs that I worked with one of my peers who's an expert at doing stadiums around the country and actually the world, is a football stadium. So this is something way different. I've done manufacturing in hospitals, but a football stadium is a totally different animal than what I had ever seen before. And it was one of the funnest projects I worked on. There's a lot of things when you do a stadium that you have to consider when doing the design. One of it is where you're going to mount the access points. With this particular stadium, it was easy for the most part, but there's a lot of college stadiums out there that don't have places to mount the access points, and that can create a big problem. One of the big reasons we did a redesign a few years ago, the fan experience. It's the fantasy football. People wanted to watch the fantasy football replays. And when you have, 50,000 people coming in, you have to use directional antennas. People are watering, the signal gets very much depleted when you fill up the stadium. And then the noise floor, when it fills up within a matter of 20 minutes, can drop 20 dB. So it's a very different type of a design. There's a lot of tuning required. But if you just take a look at this picture before I go into the next slide, you can see there's a lot of area to cover. You got a couple different bowls, and you have to find where you're going to mount these access points. And what this stadium, the first time they did the wireless design, they wanted aesthetics. They didn't want to see any access points, and that was important to them. Then the second time when they came, because fans were complaining, we asked, well, do you want it to work or do you want it to look good? And the second time they said, well, we want it to work. So some of the things, we did a survey of this stadium and a walkthrough to see, why didn't it work the first time? And here's just some interesting examples. They had their access points mounted vertical, and many of our access points should be mounted a majority horizontal unless you're using external antennas. They had them in a lockbox, like here's in the suite, the high paying people, in a lockbox mounted vertically with a marble or granite counter overhead. So the signal, as you can imagine, isn't going to probably work that good in here. And then here's another example. This antenna, I was actually at the game that day doing testing, and I said we shouldn't have had it mounted there. And this fan right here is not actually supposed to be there. It's an area he's not supposed to be in, but I knew it was mounted too short. This signal knocked out a whole section of Wi-Fi. So, these are things that you have to really think about and consider when you do a complex design like this. The other thing is, like, for this field, to fix some of the issues we had with wireless, down when you get to the lower bowl of the stadium, we couldn't reach it very well from the mounting point above. So in order to get Wi-Fi down there, we had to have special access point housing cases. And as you can see, these are mounted on the handrails, and there's actually two access points in this mounting device. One goes this way and then one goes this way, and they go in about, when the stadium's full of people, it'll go in about 8 to 10 people. And in order to do all this work, the home team had to be gone for 2 weeks. They actually had to do what's called directional boring to bore up the stairs to pull the Ethernet cable to this to power up the access point. So it was very, I've never seen anything like it, but it was very interesting. Here's some other examples of mounting and do aesthetics, like our external antennas. As long as you use non-metallic paint, you can paint them to match the environment. And then here's an example. These access points can cover, we had a dual 5 gigahertz access point. So you have two 5 gigahertz radios, and we're able to cover two different sections using external antennas. This is an under the seat mount we did not use in the stadium, but a lot of college footballs actually have access points that you can mount under the seats. And then this is what it looks like, the macro view. These are little red dots. Those are those handrail APs, and they point into the sections in the lower bowls. So we had 3 on each side, and then this blue one, it's a directional up top that shoots down about halfway. And this antenna is called a stadium antenna, and it was actually designed to cover about the equivalent of the size of one section, because what we want to avoid in a stadium is co-channel interference and bleed through into the other sections, because as you guys I'm sure know, wireless is half duplex, and if you're hearing an access point on the same channel and somebody's talking on that channel, then you have to pause. And that's the challenge, like with the stadium. There's, in the entire stadium, there's about 1,000 access points. And the channel plan is very critical. So we use 20 megahertz channels. We tune the power. Compared to traditional wireless, where you can set it and forget it, this required a lot of manual tweaks. I mean, we went during 7 different games. We had a team of 10 people walking around and sitting in every possible worst case scenario. For example, right here, you wanted to sit in the middle of the area where it would be the worst to test that the signal worked. And I could actually stream Netflix during the middle of a game. And then the other thing that you have at a stadium, all around it, you have the food carts that have a wireless work group bridge, because many of them had Ethernet connections and they could not connect wired. So you'd have to put in a wireless bridge so that the point of sales would work. But essentially, that's all I have, Brian, and I'm going to turn it back over to the next person.
That would be Matt Virus. Matt, you out there?
Matt, you're on mute in the session, in the event center.
I got it. There we go. You guys able to hear me now?
Yes.
All right. Thank you very much. Hey, everyone. Today I'm going to talk a little bit about bridging the digital divide, talking about what that means and why it's so important. So in 2020 and in 2021, it's been really a new world for all of us in 1,000 different ways, but especially for students and for education, and especially in areas that don't particularly have good broadband infrastructure and don't have access to bandwidth. We have remote learning becoming the new normal, classes from our living room, and multiple students in a family maybe having multiple classes at the same time creates a lot of challenges for online learners. 59% of lower income families have issues with bandwidth availability and have issues doing online school. Real-time video streaming from teachers to students and students to teachers just isn't possible in a large part of the United States because the infrastructure just doesn't exist. Roughly 25 million students and households in the United States do not have internet at all. And as we all know, critical learning in our society is critical, and part of the things that we need to be able to learn effectively is bandwidth, especially with the way things are now learning remotely. There are a lot of ways to get funding to fix these issues for government agencies, for schools, for state and local governments. There's CARES funding in the United States. There's lots of funding programs all through the world where there is state and local government funding available to address some of these issues and some of the cost of addressing these problems. So here's something that we kind of cooked up that we've deployed in a few places. So we have a collection of products that do wireless backhaul, hardened industrial switching, and wireless connectivity. And all of these products are hardened. They're meant to be outside. They're able to be installed in harsh environments. They're able to get wet, to get hot, to get cold. The purpose of this is to be able to stand this up quickly, to be able to have high bandwidth, low latency connectivity that blankets a town or blankets an area of a town or blankets a neighborhood, something like that. So the solution are wireless backhaul from fluid mesh, or as it's called now, ultra reliable wireless backhaul. Fluid mesh, you can think of it as wireless fiber in places where we're not able to run fiber because of cost, because of the time of needed to deploy it, because we just don't have the funding, we don't have the time to wait. You can pin up a fluid mesh solution or an ultra reliable wireless backhaul solution very quickly. It takes just a few minutes to stand up. It's a line of sight wireless deployment that is not client facing. So fluid mesh endpoints and radios talk to other fluid mesh radios, and they have an Ethernet handoff. From that Ethernet handoff, we're able to run into an industrial Ethernet switch that can be powered via AC, DC, multiple ways to power it. And from that switch, we're able to connect to cameras, wireless access points, or any other sort of public safety, public infrastructure device that needs connectivity. Primarily in the use case that I'm talking about for a few deployments we've done, the endpoints have been wireless access points, strictly speaking, Meraki MR86 wireless access points. Then over top of that, we're able to layer Umbrella and be able to have a very, very controlled, very policy-focused security framework that's in alignment with the policies that our schools and our state and local governments are doing at their head ends. The primary place we see this being used is in a few of the case studies I'll go through. We have a school building that has high bandwidth and has a lot of availability of internet service, but we have a community that does not have infrastructure in place. So we're able to safely, securely extend that bandwidth from the school using fluid mesh and using Meraki wireless access points through the community, and to be able to give parents, teachers, and students a real comfort factor in knowing that the internet that these students are accessing from home is the same experience they get when they're at school, through Umbrella, through other security services that we're able to layer on top of it. Just like we're able to do at school buildings, we're able to give the same sort of experience and the same sort of quality experience both in terms of speed and availability, but also in terms of content filtering and policy impactment that we're able to do at the schools as well. We're able to extend everything, have it be fiber free, do this quickly, low cost, allow students to do everything that they would do at home just as they used to do it at school. So here's kind of what it looks like. We have a in the center, we have the school where there is a fluid mesh base station. From that base station, we're able to send an encrypted wireless signal that's received by another fluid mesh endpoint out on a light pole. We're on top of a grain elevator. We're on top of any sort of public infrastructure where we can get permission to put some of these devices. Then from that light pole and with that fluid mesh endpoint, we run into a switch. We connect to an access point, and we're able to broadcast our public Wi-Fi network from there. Fluid mesh is able to connect point to point and point to multi-point. So we can take our base station and connect it out up to 3, 5, 6 miles to connect to the next fluid mesh endpoint. From that endpoint, we're able to connect out to another and another and another. So we're able to go from fluid mesh endpoint to endpoint and hop without losing bandwidth, without adding latency as we hop to different light poles that are potentially miles apart, and able to really get a very good penetration into the area. And then we're able to layer our Wi-Fi access points on top of that fluid mesh backhaul network to reach out to a large number of students. So one case study we did in a school district, this was a school in Texas. The challenges were to reach into an area of the town that had not a lot of bandwidth availability and not a lot of funding, and to do that quickly. This was a situation where digital learning had started, and after digital learning started, there was this observance that a lot of the students weren't in class or weren't able to go to class because they didn't have bandwidth, and it just didn't work. Times where they had tried to deploy LTE hotspots, the bandwidth would get chewed through really quickly, just in a couple days, because kids were using Netflix or YouTube and using all the data up, because that policy enforcement around what data gets through, that policy enforcement that exists at school wasn't in existence on those hotspots. So we had this real challenge where we're bandwidth challenged, we're funding challenged, and how do we do this? So we came up with the idea to use a whole bunch of fluid mesh radios, connect a bunch of Meraki APs to them, and as quickly as possible, stand up fluid mesh endpoints from the school out to the community, layer the APs on top of them. So the initial phase that was completed was to pull out 47 identified student homes in areas that were severely underserved, and the end goal is to get to 100 student homes serviced within 100 days, and have that all deployed within 30 to 60 days. It was a great success. Things have gone really well there, and we're scaled out to where we're projecting to cover the entire town now, most likely by the time the fall semester starts again. So moving on to another case study. This is an actual city that was looking to create a multi-use network. So part of the challenge of this city was having was much like the previous city, where there are underserved households and households that don't have access to bandwidth. So that was kind of the primary driver for this. So it was several hundred fluid mesh radios stood up the same way in public buildings where there's fiber and broadband available. Bridge that out into the community and pipe it around wherever it needs to go. Using Cisco 3300 switches, they're industrial Ethernet switches. They're hardened. They can be installed right on the light pole. And from light pole, we're able to connect up Meraki APs. Now, in addition to serving low bandwidth areas and cities that are underserved with broadband, we're able to do other things. This is kind of a if you build it, they will come situation. Once the network is stood up and it's running, and we are able to enable these digital learners to connect and to get into class, we start talking about what else can we do with this bandwidth. And we start talking about smart parking meters. We start talking about traffic control that's smart and interactive and able to have a high bandwidth, low latency connection to stream footage of traffic congestion and traffic flows. We're able to equip some of our public servants, our police officers, our fire departments with high-speed connectivity wherever their trucks go. So there are a number of things that the city is able to realize from this initial deployment that was projected at enabling online learning and meeting the needs of some families with respect to the digital divide challenges of school and classroom use. So some details of how this looks. So here's a general map of one of the cities where we initially deployed this. We have if you can see on the left side, we've got a building where there's high speed fiber access to internet, maybe 1 gig or 10 gig, and we're able to bring that service out into a fluid mesh base station. And then from a single fluid mesh base station, we go out to many fluid mesh radios. From those radios, we can go into a hardened industrial switch. From that switch, we can go to multiple access points, perhaps with omnidirectional antennas or with directional antennas, kind of depending on where they're located. If you look on some of the slides, we talk about trying to have a 300-foot distance from targeted homes to Wi-Fi access point. 300 feet is kind of the targeted distance. In some testing that I've done, I've been able to connect and get a 10 megabit connection at over 1,000 feet with a directional antenna. So there are a number of things in this design that are very flexible with respect to antennas, directional antennas, omnidirectional antennas. But the point of this all is, from a single building with high-speed internet, we're able to spider out and cover a very large area of the city. We can do it very quickly, and we can do it with a very standardized hardware selection, standardized configurations, standardized optimizations, and everything can work and scale very well. So here's another deployment overview that we have, and you can see here we've got the truck on the bottom left that's actually installing some of this on the light poles as we go through the city. You can see on the top left, this is roughly where the fluid mesh endpoints are deployed. We get a really good grid covering. When the fluid mesh endpoints come online, they're able to use a proprietary protocol called Prodigy, and Prodigy is able to form a link between all of the fluid mesh endpoints, and the entire grid becomes aware. So if we have issues where one fluid mesh endpoint is suddenly unable to connect to another one, potentially because it loses the line of sight connection, it's able to find another neighbor with a strong connection and bring that link back up to another neighbor. So we're able to be very resilient with this deployment. In this particular diagram, we're showing, again, coming out of a building into a switch, into a fluid mesh endpoint, fluid mesh endpoints finding each other and peering up. And then from that peer grid overlay down into switching, down into more switching, and then into wireless. So we've got kind of a multi-tiered deployment here where we're able to potentially spider out in different directions and have a kind of a north deployment, an east deployment, and a south and west deployment where we can control the span of the peering amongst fluid mesh endpoints and get more bandwidth into certain sectors of the city. And then as we need to add more bandwidth in certain sectors, we can have kind of a pointed deployment in different directions, and we can force more bandwidth into those different areas as we need to. So it's very scalable, and it can scale fairly quickly without a lot of cost. Here's kind of another graphic looking at how we can go from the school to the light poles to the houses. And this is generally what it looks like. This is not a super technical diagram, but this is the gist of what the digital divide solution looks like. Using infrastructure that's already in place, using power that's already in place, and using bandwidth that already exists. It's just a matter of moving that bandwidth, school building, out to a community, and doing it securely with policies, and doing it with resilient hardware that's able to rebuild connections should they be impacted by line of sight availability. Some key things to look for when you're doing a deployment like this. Fluid mesh is a line of sight deployment. So you must have line of sight. We typically look for school buildings, grain elevators, water towers, public types of infrastructure that we're able to put things on. Or if you're doing it for a private entity, we're looking to get the base stations as high as possible. And we're looking to get any other endpoints in spots that do not have line of sight impacted by growth, as was talked about some of the previous presenters. As trees grow, as new buildings go up, it's important to continually be reviewing your deployments and make sure that you still have line of sight from your ideal base station to your endpoints. You don't want to have your endpoints meshing off onto other endpoints. You want them all going straight to the base if at all possible. There's AC and DC power at a lot of these power poles through the cities. Sometimes the voltage isn't quite right, so we need to use step up and step downs. Sometimes there isn't power there at all, so we need to be a little more strategic about where we deploy these things, making sure that we deploy in places where power isn't already being used for other purposes. This stuff is not particularly high power, so usually that's not a problem, but it is something to be aware of. And my mouse is being a little grouchy at me. That's pretty much all I've got today. Thanks for your time. If you guys have any questions or want any more information, please let us know. Happy to demo this, talk about the bill of materials, and go through it as you need.
Thanks, Matt, for that review. Let's kick it over to Jim Sands to wrap us up. Jim's going to walk us through university installation and insights into that. So we need to switch over to the other presentation at this time. There we go.
There we go.
Perfect.
Excellent. Hi, everybody. So I'm going to go over the Meraki solution, and Meraki is known for really making the networking management and maintenance operations very simple. And as well, let me see, how do I advance? Here we go. So one of the things we tout, we pride ourselves on is that we produce very powerful technology, but yet still very easy, simple to use. So people can truly go about their jobs and contribute to the organization's ultimate goals. And rather than being caught up managing, maintaining the technology on a day-to-day basis, they can actually work more towards the ultimate goals of the organization. And Meraki, hopefully I'll show you just a small cross section of the things that enable our customers to do that. So as Bryan said, I'm going to talk about Sweetbriar College, which is a college in Virginia here in the US, and they use Meraki extensively because like many of our institutions, they're spread very thin. The IT teams are spread very thin. They're having to manage many different pieces of equipment across many types of technology, and it's very difficult to do that when you have a very small staff. And Meraki really makes this process very easy, and at the same time provides a tremendous amount of insight and visibility into what's going on. So what I'm going to do is first jump in to show you what Sweetbriar College does on a day-to-day basis from a network and client monitoring perspective, and then we'll jump into a little bit of client troubleshooting from there. So this is the dashboard for Sweetbriar College. You can see up here is the network, SBC core network, and all the various pieces of gear that they have within their network. And first across the top, what you'll notice is this health indicator. So with Meraki in the dashboard, you'll have lots of different indicators, usage, charts, and so on, no matter where you are within the dashboard. And right across the top, this shows you the different kinds of components within the network. And if there was a problem, these would change colors and you'd see the numbers change as well. You can click on any one of these icons and move right into that portion of the dashboard that will help you immediately start troubleshooting and focusing your attention where it needs to be in order to solve a problem. Something else I wanted to mention too, that this is the Meraki dashboard, meaning that everything that you manage the product or Meraki gear from is done from this web-based interface. It's cloud accessible. Everything Meraki is cloud managed. We are part of the cloud networking group within Cisco systems, and that means it's accessible from anywhere in the world. So somebody can manage this whether they're at the campus or if they're off-site somewhere. So going back to this, we're seeing this client page. This is network-wide clients. Client view is very important in Meraki because we want to focus on the customer, the client who's actually using the network resources, as well as their tools, which happen to be the applications. And I'll jump into that a little bit very shortly here. But we also notice here that we can change this time span when it comes to monitoring. Currently, we're looking for the last day, but if we can go back for 30 days, and then we'll see usage charts like this across here. For instance, if we do see a big spike or a change in the network traffic, that might call our attention to something else that's going on. Now, down below, we could see how the clients are actually connected to the network, whether they're plugged into the network via a wired connection into a switch or over the wireless. If they're VPN'd in using the Meraki Systems Manager, Enterprise Mobility Management Solution, then you'd see a different icon as well. And then we also learn about the name of the device. So all Meraki hardware will begin to fingerprint the traffic and learn what's going over the network. And in this case, we see the host names or the device names. This is coming from NetBIOS names or the multicast DNS. And that's how we learn this information here. And so it gives us more insight and a better understanding of who's actually on the network. Now, we can also learn operating systems and so on. But in Sweetbriar College's case, their dashboard needs to have additional columns. Needs to be customized more, and you can do that through this little wrench right here. They've added onboarding, the onboarding and performance columns, which we'll talk about quite a bit about the wireless experience. We also see this user information. So not only the device, we want to know about the user, as well as connected to where the users are actually connected into the network. So now that they've added the columns, the person who's in the dashboard monitoring and maybe on the help desk taking trouble cases, they have a much better sense about what is going on. They know the actual users. So assuming they're using radius authentication, not only do we learn the device name through that Meraki fingerprinting process, but we also can tie the username to the device. This is very important in places like K through 12 education, where they are using multiple shared devices. So they might have a rack of iPads. However, they have generic names. So how do we know who's actually using that particular device if there's a problem? And so that's a great way of doing that. We see usage. Now, this is going to be important when it comes to gaining more awareness about the type of traffic. We'll talk about that soon from the application perspective. Then also the onboarding and performance columns over towards the right. These are focusing just primarily on wireless. And what those are giving the network operations team and help desk people an immediate sense of what's going on within the wireless network. In other words, onboarding is how are the users, the experience of the users when they actually get onto the wireless network. And then once they're on the wireless network, how is it performing? And so if you look down a little bit further, they will color code them about midway down. You'll see that where it says 50%, a little yellow dot there. We could see that that particular user at Cheese Room has had some problem getting onto the network, and we'll talk about that more extensively, what all that means. But then also once they're on the network, they seem to be performing just fine. And then the last column on the right there is the connected to column. And so putting all these pieces of the puzzle together, this gives the Sweetbriar College staff a greater sense of awareness as to where they need to focus their attention if there is actually a problem on the network. So I mentioned before, actually I'm going to go back one slide, I'm sorry. I mentioned before about the applications as well. So Meraki takes advantage of the Cisco NBAR2 library, the network-based application recognition library. So we have access into visibility into over 1,400 different applications that we can learn what's going on our network, but also we can build policies. So all Meraki access points support layer 3, 4, and 7 firewalling capabilities, as well as traffic shaping. And that's going to become very handy when we think about the usage and types of applications on our network. And if I were to click that little more button underneath the pie right there, we can learn much more about the applications and get a better view of the overall usage per application. And we could see in this case, Netflix is in the top 10 of applications. And while the usage is not as great right now, and that's because of COVID, not a lot of people on the campus at Sweetbriar College, that generally floats up higher. And then Netflix, while it's a nice to have and it's very important for college students, we also have to be careful about making sure that streaming video and streaming media doesn't consume all of the internet bandwidth, so for other purposes as well. So maybe we want to build a traffic shaping policy, or maybe Sweetbriar College would want to build a traffic shaping policy across, and a blanket policy that affects everybody, or maybe they want to just really focus on the top consumers. And if I were to click on that application right there, you can actually drill down and see all the users for the Netflix application. You can see all the different users that are using that application. If we find, or if they find that a majority of people don't really use Netflix all that much, except for a few, maybe just apply a traffic shaping policy to that user or a handful of users, or maybe it's just better to build a blanket policy that would affect everybody. Okay, so now that that's from the more of just the monitoring of the network as well as the clients. Now, how about troubleshooting? With the client monitoring, if we were to click on one of those clients, we'll dig into the troubleshooting from there. But first, when a user, I mentioned before about that onboarding column, when the users get onto the network, what is the experience like? Are they having a hard time? And we have tools, and I'll show you that very soon. Once they're actually connected, is it a good experience? And if not, what exactly is causing a poor experience? And then we also have a greater sense of how the actual network components are operating. Are the access points overloaded, or do they need optimization? Perhaps the RF design was not, or the radio frequency design was not as good as we wanted it to be, or maybe somebody made a change. And so we need tools that will help us narrow that down. So if I were to click on one of those clients back in that client view on that client page, in this case, it's Franny's MacBook Pro Air. You can see toward the center at the very top, and I'm in the overview section. So let's say that Franny calls into the Sweetbriar College help desk. Is complaining that that the access is very slow. One of the first things we want to do to check the signal levels, the signal to noise ratio. And we'll give you a color-coded meter right there. If it's green, it's generally pretty good. So we know that that's not a real problem. Something else I want to point out also is that in more advanced troubleshooting situations, all Meraki gear will give you the ability to run packet captures. If you were to click on that link, that little link right there, it will actually launch or take you to a page that will give you the option to launch a packet capture, download it as a PCAP file, and then analyze it further. The filters are put in place for that particular client on that particular access point, and so it makes troubleshooting very easy. But usually this is used by Meraki support, but it certainly can be used by any of the customers. Now, something that we've added relatively recently is this current client connection, which gives the network operations team the visibility as to how that client is connected into the network and walk through the network. So we can see Franny's MacBook Air is connected to the Grammar 110 access point, which is connected to upstream to the Grammar switch number 1. And that little number to the left of that is the port number that the AP is plugged into. And then so on, if you could follow it up the line. And perhaps the slowness problem is not actually caused by the wireless network at all. Perhaps there's a problem upstream. We might have a bad cable. In that case, one of those little green dots with the check mark might turn yellow, or it might even be red. You can hover over any one of those icons and you'll get additional information. And you can do all this from a single point. And that's part of the Meraki simplicity and the Meraki health features. A little further down, we show you some summary health widgets to give some good summary information from a client latency perspective, as well as are they even having a hard time getting onto the network. And then just like on that first page I showed you about with the applications, you see there's still a pie chart for this particular user though. So now we can see exactly what kind of applications this user is using. And in this case, we see it's very small, but you can see that Netflix happens to be the #1 application that Franny's MacBook Air is using. What's nice about this is that we can learn about the IPs, the domains, but also if you're doing investigations from a security perspective and we see IP addresses that may be determined malicious. You might actually be able to see that in this field area as well. So
and,
moving,
James, just a quick note for those of you that do need to drop at the top of the hour. We're going to go ahead and start a poll on the right-hand side. I know some people might need to leave at the top of the hour. With that, James, just keep presenting. Thank you.
okay, great, thank you. So next, the next tab over, I'm still with Franny's MacBook Air. And you can see I moved over to the connections. Now this relates to that onboarding column that we saw earlier on the original client's page. And so how is the user actually having a hard time getting onto the network? And if so, where is the problem occurring? What's nice is we actually narrow this down by SSID. So we immediately save a lot of time troubleshooting as to where the problems might occur for this particular user. And then also the individual steps of what is required to get onto the network. So we see association, can the client associate to the AP? Then authentication. That's usually where we see the highest number of problems, but if there's an authentication problem, it's usually a password problem, perhaps a server's down, a Radius server, but nonetheless, we'll be able to see that for this user. Then we see DHCP, can the client get an IP address? Or in this case, we see it's a yellow color, and that means that, hey, we've had a higher number of problems with DHCP. Maybe the server response is slow. Maybe there is potentially a purposeful or accidental rogue DHCP server on the network, and this is a broader problem affecting more people and what have you. So we can actually tell a lot of what's going on a wider scale. Then the next one is, can we resolve host names with DNS and then ultimately get out to the network? And then at the very bottom, you'll see that we provide a historical list of the different access points that Franny's MacBook Air touched or connected to. And so we can go back in time and follow these problems. And because usually when wireless problems get called in, it's after the fact, it's not real time, and we need to go back and retrace our steps. Now, the performance tab is the next tab over. So once we're on the network, how are we actually performing? And we can see the signal quality for this particular user, as well as the average latency on the graphs on the left side toward the middle and bottom. Importantly, what I want to point out is that blue bar across the bottom of each one of those graphs, which are all time synchronized, indicate the access points that the user is connected to at a certain point in time. So as that user roams, then we can see if a problem moves to a particular access point. And if you hover over that point in time, you can see where those access points are and follow which one might have had the problem. And now I know this is a little bit of a cluttered or noisy slide here, but a little further down on that same screen within the performance area, we can also relate those client experience or metrics back to the access point. So we see the AP channel utilization. If we happen to have a high client latency and a high channel utilization, that might be the problem. Or the AP usage. Perhaps there's a huge amount of throughput going through and we see lots of clients connected. Then perhaps the access points need to be tuned. Maybe something is not operating properly in the area. And then lastly, we bring all this information together in this history tab across the top in a very human readable fashion. And we help the user, the help desk and engineers troubleshoot the problem. We see in the top case here, there was an authentication problem, and then we're giving you suggestions as to how to solve that problem. The other case below it, we see there were problems during association, and that could be related to RF problems. We even give you links in the dashboard as to where you need to go to check to see if there is a problem with the configuration or if you do need to make a change. And with that, that is the end of my portion. Bryan, I'm going to turn it back over to you.
Awesome. Thank you, Jim, for running through that. Thanks to all the presenters today. Really appreciate your time and your insights. Hopefully, to all of you out there, a lot of really great questions in the Q&A panel. We've been trying to keep up, but hopefully this gives you some idea as to the different ways the wireless is used across multitude of case studies, use cases, businesses, and hope you enjoyed it.
Thanks, Brian, and thanks to all of our presenters. Thank you guys for taking the time. I know you're super busy out there supporting all of our customers. I love the fact that we were able to see these case studies. I think it's one thing to see the technology, but to see how it's implemented, where it is, what are some of the problems, and I always love the how not to mount a AP, so that's always fun. So thanks everybody for joining. On the right-hand side, you guys should still see the poll. It should be open. Let me double check. It's open for another 5 minutes. If it didn't pop up because you had Q&A up, very bottom, there's 3 little dots. If you click on those 3 little dots, you'll be able to click onto the polling. Also for this group, remember we have one other session coming up on Thursday, noon Pacific time. I'll let you try to figure out what that is in your local time. We have a session called From Netacad Student to Network Engineer, basically. So we have 3 for our person here from Meraki. We have 3 people that work for Meraki that had previously been Netacad students. They're going to share their journey with you. So that link has been provided to your instructor as well. So if you're a student, your instructor should have that link. And hopefully we'll see you again on Thursday. So we'll hang on as the poll finishes up. We'll let all of our presenters go so they can head off to that next meeting that we all have on our calendar. Thank you guys. This is great. Thank you for supporting Cisco Networking Academy instructors and students today.
Thank you, Echo. I've gone ahead and saved the chat and Q&A for you, so I will send those over as soon as we wrap everything up. And once the poll closes, I will go ahead and save that for you guys as well. And I'm going to go ahead and stop the recording.